Have you ever thrown a stone into a still pond and watched the ripples spread out? Now, imagine that happening not with water, but with the very fabric of space and time itself. That's the mind-bending reality of gravitational waves. These are literal ripples in space-time, caused by the most violent and energetic events in the universe. For 100 years, they were just a wild prediction in Albert Einstein's theory of general relativity. He imagined that massive objects, when they accelerate, should create these tremors. But he thought they'd be so faint, so impossibly tiny, that we'd never be able to detect them. For decades, the universe seemed silent to us in this regard. But it wasn't silent. It was humming, vibrating with the echoes of cosmic cataclysms. We just needed to learn how to listen. This isn't just an abstract idea. The universe is constantly being stretched and squeezed by these waves. The distance between you and the screen you're watching is, right now, fluctuating by an amount smaller than an atom's nucleus, all because of a black hole merger that happened billions of light years away. For a century, finding proof of this was one of the biggest challenges in physics. It was like trying to hear a single pin drop in the middle of a hurricane. The signals were buried in the noise of our own planetary car. Every earthquake, every tiny vibration on Earth could easily mask the subtle whisper from the cosmos. Scientists knew they needed an instrument of almost unimaginable precision, a cosmic ear that could filter out all that noise and tune into the symphony of space-time itself. The story of how we finally heard them is a triumph of human ingenuity. It brings us to the Laser Interferometer Gravitational Wave Observatory, or LIGO. Picture this: two giant L-shaped detectors, one in Washington State and one in Louisiana, thousands of kilometers apart. Each arm of the L is a 4-kilometer-long tunnel. Inside these tunnels, a powerful laser beam is split in two, with each half traveling down one arm. At the end, mirrors reflect the beams back to the starting point, where they recombine. Normally, these two light waves should perfectly cancel each other out. But if a gravitational wave passes through Earth, it will stretch one arm and squeeze the other by a fantastically small amount. This tiny change means the two laser beams will no longer be perfectly in sync when they return. They'll create an interference pattern, a flicker of light that our detectors can see. To give you a sense of the scale, LIGO is designed to detect the change in distance 1/10,000th the width of a proton. It is the most precise measuring device ever built by humanity. And on September 14, 2015, it worked. For the first time, both detectors registered a signal. It was a faint, rising tone that lasted less than a second, a sound that scientists affectionately call a chirp. After a century of searching, we had finally heard the universe speak. The team analyzed the signal, and the conclusion was staggering. The chirp was the sound of black holes, each about 30 times the mass of our sun, spiraling into each other and merging into one. This event, which happened over 1 billion years ago, released more energy in its final moments than all the stars in the observable universe combined. All of it radiated away as gravitational waves. Since that first historic detection, LIGO and its European counterpart, Virgo, have heard dozens of these cosmic events. It's like we've suddenly developed a new sense. We've heard the death spiral of two neutron stars, the incredibly dense corpses of massive stars. Their collision was so powerful that it was also seen by telescopes across the globe. In a flash of light and radiation, this marked the dawn of a new era called multi-messenger astronomy, where we can both see and hear the same cosmic event. Getting a complete picture for the first time, we can now listen to the universe's most extreme phenomena. These waves are telling us things we could never learn from light alone. Light can be blocked by gas and dust, but gravitational waves pass through almost everything. They are a direct probe into the heart of the most violent events imaginable. So what secrets are these ripples in space-time revealing? First, they're giving us an unprecedented look at black holes. Before LIGO, black holes were mostly theoretical objects. We knew they existed from the way they affected nearby stars, but we'd never directly observed them interacting. Now, we are routinely detecting their mergers. We're learning how many there are, how big they get, and how they grow. We're reconfirming that the no-hair theorem is true, that a black hole is defined only by its mass, spin, and charge. It's like testing Einstein's theories in the most extreme laboratory in the universe, and so far, he's passing with flying colors. We're essentially creating a census of black holes across cosmic history, piecing together the life and death cycles of the universe's giants. But the potential goes far beyond black holes. Gravitational waves could be our ultimate time machine. The furthest back we can see with light is to about 380,000 years after the Big Bang. Before that, the universe was a hot, dense plasma, opaque to light. But gravitational waves could have been traveling freely since the very first moments of creation. If we can detect the primordial gravitational wave background, the leftover vibrations from the Big Bang itself, it would be like seeing a baby picture of the universe. It would open a window onto the first trillionth of a second of existence, a time when the fundamental forces of nature might have been unified. This is the holy grail of cosmology, and gravitational waves might just be the key to finding it. The future of this field is incredibly exciting. We're already planning the next generation of observatories. On the ground, projects like the Cosmic Explorer and the Einstein telescope will be 10 times more sensitive than the current LIGO, able to detect every single black hole and neutron star merger in the entire observable universe. Imagine a daily weather report for space-time, charting the cosmic storms as they happen. And then there's LISA, the Laser Interferometer Space Antenna. This will be a space-based observatory with 3 spacecraft flying in a triangular formation, millions of kilometers apart. By moving into space, LISA will escape the noise of Earth and listen for much lower frequency gravitational waves. These are the slow, rumbling bass notes of the cosmos, produced by entirely different sources. LISA will be able to detect the gentle hum of millions of binary star systems in our own galaxy, creating a 3D map of the Milky Way. It will hear the mergers of supermassive black holes, the behemoths that lurk at the centers of galaxies, with masses billions of times that of our Sun. Their collisions are cosmic train wrecks that reshape the galaxies around them, and LISA will give us a front row seat. We might even detect exotic objects like cosmic strings or listen to the echoes from phase transitions in the early universe. We're on the cusp of discovering phenomena we haven't even imagined yet. Each new window we open on the universe has led to revolutionary discoveries, and the gravitational wave window is the widest one yet. This journey is about more than just astronomy. It's changing our fundamental understanding of reality. We used to think of space as an empty, passive stage on which the events of the universe played out. Now we know that space-time is a dynamic, active player. It can bend, it can stretch, and it can ripple. Gravity isn't a mysterious force pulling us down. It's the curvature of space-time itself. We live in a cosmic ocean, and we are constantly being buffeted by waves from distant, ancient shores. These discoveries are a testament to human curiosity and our relentless drive to understand our place in the cosmos. We are no longer just looking at the universe, we are listening to its very fabric. The quest is far from over. There are still so many mysteries waiting in the gravitational wave spectrum. What creates black holes of certain mass? What happens to matter when it's crushed inside a neutron star merger? And what can these waves tell us about the nature of dark matter and dark energy, the 2 biggest puzzles in modern physics? We have just begun to tune our cosmic radio, and the universe is broadcasting on countless channels. Each new detection brings us closer to a complete picture of the cosmos, from its fiery birth to its ultimate fate. We're living in a golden age of discovery, where the deepest truths about space, time, and gravity are finally being unveiled. Thank you so much for watching. If you're as excited about the future of astronomy as I am, make sure to like, subscribe, and hit that bell to join us on our next journey into the cosmos.